Hi, welcome back to Data Science for Ecologists in R. My name is Ruairi Josifek, and this is the second of 3 videos in which I discuss polynomial regression analysis. This installment will focus on the test assumptions and the use of raw versus orthogonal polynomial transformations. So picking up from where we left off, what you're now looking at is the fit, summary, and plot of the polynomial regression model fitted to the simulated data from the previous video. As was discussed there, and is presently shown by the model formula, the polynomial regression is a form of the multiple linear regression, and so the reliability of either model therefore depends on the fulfillment of the same statistical assumptions. We can confirm or refute most of these with reference to the model residuals, i.e. the deviations between corresponding predicted and observed response values, which can be thought of as a sample of the true error distribution. For example, this residual value would be approximately 10, and this residual value would be approximately -9. So, which statistical assumptions need to be fulfilled to comfortably rely on a polynomial regression model? Firstly, the model is assumed to be linear, which, as presently highlighted, does not explicitly require linearity between the x and y variables, but rather that the ith y value is a linear function of the ith x values plus the corresponding errors. Second, the error distribution is assumed to be normal. Third, errors are assumed to be homoscedastic, meaning that they have equal variance along the predictor variables. And finally, it is assumed that errors are independent of one another. So each of these assumptions can be assessed visually using residual diagnostics plots, which are called using the base R plot function, by passing the name of the model object as the first argument and the index of the desired plot as the second argument. For example, linearity can be assessed using the first diagnostic plot, called the residuals versus fitted plot. As the name suggests, this shows us the residual values plotted against the corresponding predicted values of our response variable. In the case of linearity, data points are centered on 0, illustrated by a horizontal red line at approximately y equals 0, as is shown here. Normal distribution of errors can be assessed using the second diagnostic plot, called the QQ or quantile-quantile plot. This compares the quantiles of a theoretical normal distribution to the quantiles of our residuals, following standardization to the same range as the theoretical distribution. Normality of the residuals distribution can therefore be confirmed when data points closely follow the diagonal line, as is again shown here. Homoscedasticity of errors can be assessed using the third diagnostic plot, called the scale location plot. This is like the residuals versus fitted plot, except that the square root of the standardized residuals rather than the raw residuals are plotted. This transformation compresses the residuals range in such a way that helps to elucidate subtle changes in variance along the predictor variables that may be hidden or exaggerated by outliers in the residuals versus fitted plot. In essence, the spread on the y-axis is the residual variance relative to the expected variance. In the case of error homoscedasticity, a horizontal red line is again present, as is shown here. Independence of errors can also be assessed using the first residuals versus fitted plot and is confirmed by a lack of discernible pattern or grouping in the data points, as is the case here. So for examples of diagnostic plots showing assumption violations, I encourage you to go and watch our earlier videos on checking the assumptions of a linear model, the link for which is provided at the end of this video. Finally, an assumption concerning the predictor variables, which is particularly relevant to polynomial regression, is a lack of multicollinearity, which brings us back to the topic of raw polynomial transformations. But first things first, what is multicollinearity? So in the context of multiple linear regression, this concerns the correlation of 2 or more predictor variables. While in the current context of polynomial regression, multicollinearity particularly pertains to increasing levels of correlation among higher-order polynomials of the same predictor variable. This is an inherent limitation to the use of so-called raw polynomial transformations applied directly to the x variable, since x cubed equals x squared plus x, and so on. Multicollinearity results in unstable coefficient estimates, whereby small changes in predictor variables impact large changes in the calculated coefficients. An additional symptom is inflated standard errors, which in turn increases the risk of type 1 error, whereby a true null hypothesis is rejected. We can check for multicollinearity by calculating variance inflation factors, or VIFs. These are derived per predictor variable by first regressing the kth predictor on the remaining predictors and then calculating the inverse of 1 minus the resulting r² statistic. Since this would be cumbersome to compute manually, we can make use of the OLS_VIF_TOL function from the OLSRR package by simply defining the model object to be analysed. This returns a data frame containing a tolerance and VIF value per predictor variable, where tolerance is the name given to the denominator term in the VIF formula. VIFs greater than 4 are generally considered to be indicative of moderate multicollinearity, with values of 10 and 1 indicating extreme and a complete lack of multicollinearity respectively. So in this case, there's absolutely no cause for concern, and we can now, moreover, confirm that the assumptions of the model have been met. However, should you observe VIFs greater than 4, then orthogonal polynomials can be used to overcome multicollinearity. This can be specified within the nested poly function by defining the raw argument as false. Users should, however, be cautious both of overfitting and of the change in interpretation of resulting coefficients. Since orthogonalization eliminates correlation between different polynomial transformations of the same predictor variable, additional polynomial orders will continue to improve the model fit while running the risk of masking true mechanistic responses by better capturing the noise or errors in the training data, especially in situations with limited sample sizes. So let's look at an example from R to illustrate the change in interpretation of coefficients for raw and orthogonal polynomial transformations. Using the same simulated data, we can compare summaries of the original raw polynomial model and a replicate model fitted using orthogonal polynomials, specified as discussed. As you likely suspected by now, the coefficient values between the models vary considerably. However, the residual distribution summaries and statistics both tell precisely the same story. Furthermore, as is shown in the plot, both models predict the same response value for any given predictor value. So since raw polynomial transformations are applied directly to the predictor variable, interpretation of such fitted coefficients are similarly direct. As with a simple linear model, beta 1 can be interpreted as the change in y per unit increase in x, since this is the linear component of the polynomial model. Meanwhile, beta 2, the quadratic component, can be interpreted as the instantaneous rate of change in y when x equals 0. Since orthogonal polynomials require an additional level of transformation and are thus no longer directly linked to the pre-transformed predictor variable, resulting coefficients may not be interpreted as effects on y. So despite potential problems with multicollinearity, this may seem like an argument for the use of raw polynomials. However, it may equally be suggested that the instantaneous rate of change in y when x equals 0 is not typically relevant in the context of ecological research. Moreover, as well as the discussed advantages of the elimination of multicollinearity and increased numerical stability, the use of orthogonal polynomials facilitates the partitioning of variance captured among the various transformed predictors, and this is where we will pick up from next time. So, until then.